Hello my friend, welcome to another video. Today is gonna be finally linked list. We're gonna tame this tricky concept in computer science. Here I just want to show you this public Notion page that I am building in the spare time. Here you can find a lot of good sources or a lot of good links. For example, for today's code, you have all this jazz that you can digest. I leave a link in the description. This is not a snake oil link. Nobody wants to sell you anything. And yeah, let's just jump into the code. This is gonna be a highly practical kind of video. I will give you just the minimum viable theory to get through some exercises that we are gonna do together. Because I don't really believe anymore in getting a lot of theory without the practice. I don't really believe anymore into that. So if you wanna know more about linked lists, I highly suggest to you these linked lists for absolute beginners from Code Vault. So like in all my videos, I suggest you this channel, which is really well done. So there's no point on me to make this stuff again. Here we're going to start from the very beginning, and the approach is going to be highly visual, because I think to understand linked list, you really need to visualize these nodes, this chaining, everything that happens. Because if you see only the bare bone code, it's very tricky in my opinion. First question, what is a linked list? Well, we can say that a linked list is just a fancy array. It's just a different way of storing data in a more flexible, annoying way. So let's build this understanding from the ground up. Here I will just define a pointer and assign the value null. So in my stack, I will have a 8-byte pointer with the value null. Okay, a pointer that is pointing to anything. Then I say v is equal to malloc size of int. So the malloc is gonna give me back a pointer to 4 bytes, right? Depending on the system, but we can assume that an integer is 4 bytes in the heap. So the scenario is this. Now my pointer has this value and is pointing in the heap. What are we gonna do with that? Well, I simply say at v is equal to 42. Easy peasy, right? Now, what if I want to create a chain of integers, right? In the same vibe of an array which is just a cluster of contiguous numbers or whatever data type. Well, an integer is not the correct data type, right? Because an integer doesn't have a pointer to the next element. That's exactly why I need to create a chain. Here you can say, well, you just malloc size off of 10 integers and you have an array in the heap, but that's not the point, right? We want to recreate a linked list. How do we do that? To do that, an integer, as we said, is not the correct data type. We're gonna create our own quote-unquote data type, which is simply a struct that contains, in this case, a number, the actual integer, and then is gonna contain a pointer to the next element, as you can see here, right? Struct as node, which is the element itself, so it's kind of recursive. Let's have a visual understanding of this data type, this node. Is this block that contains nb, the integer, and as a second member variable, a pointer to the next element, just a pointer to another node, which is exactly the same. Okay, so this is the minimum viable struct to create a linked list. It has to contain some data, in this case only one nb, integer nb, but it can contain a lot of stuff. It really depends on you. And then it has to contain a pointer to another element of the same type. That's the minimum viable data to create a linked list. When we say node in computer science, we simply imply a structure that contains data, right? This is just convention. Now the question, why does next is struct as node and not type node? Legit question, right? And this is a very often made mistake. Well, the thing, it's pretty simple. The first code that is gonna be run is this one. The first thing that is going to happen is that you're gonna declare this struct, right, as node. That's the first code that is going to be run. Only in a second moment, we're gonna have the typedef that is gonna take the actual struct and say, hey, this big boy here, call it type node. So that's why inside the struct definition, I cannot put type node because it doesn't yet exist. This is going to happen on a second moment, all right? I think it's simple. Now let's get into business. Let's start to do stuff. Now with this node, we're going to create our beautiful linked list. As you can see, you have the stack visual and the heap visual. So we start our code. I'm going to declare 3 pointers to nodes, node 1, node 2, and the first node is going to be called root by convention, or head. It really, it's up to you. Then I'm going to say, okay, root is equal to malloc size of type node, and I'm going to do the same for node 1 and node 2. So what is going to happen? Well, malloc is going to return pointers in the heap for a node. So you get this scenario, right? You get 3 nodes in the heap, and in the stack we have 3 pointers to those nodes. Easy peasy. As you can see, I've used mnemonics, hexadecimal values. We have bad food, cafe baby, and dead beef. These are magic numbers, magic hexadecimal numbers to ease the life of reading different addresses, right? So we can immediately see what we're talking about. Then what do? I say root and b equal 42, node 1 and b another number, and so forth. So this is what is going to happen in the heap. I'm going to assign the values, and easy vanilla now. And then the thing, I'm going to say root next is equal to node 1. So what is going to happen? I have my bad food node that now will point to the actual next node, which is node 1, because I'm going to assign to the next pointer the value of node 1, which is cafe baby. So you have this visual inside the heap, right? We do the same accessing all the elements with root. So I do root next is equal node 2. So node 1 is going to take as a next pointer dead beef, which is going to be the address of the last node, right? Node 2. So it's going to point there. And then at the very bottom, I'm going to say root next is equal to null. So the last node is going to get the value null. As you can see, I managed effectively to create my linked list in the heap. And I have access to all these elements thanks to root. Of course, this is just a pedantic introduction, right? I don't have to have node 1 and node 2. I can use malloc directly on the node. I don't need to stock a pointer to these elements in the stack. Just to have a visual understanding of what is a linked list and how we can create that. The thing is that we can access all the elements thanks to root, right? Root next, and so forth. So that's the gist of a linked list. It's a structure chained together thanks to these pointers, all right? Now I want to show you how to iterate, how to get all the elements which are inside my linked list. So let's start with our visuals. We're going to start by creating an array with the value I, right? So this is a char array. As you can see in my stack, I have these chars, and the final char is going to be the sentinel value \0, right? This is what happens when you initialize a char array. Then what I'm going to do, I'm going to create my linked list. So I have my root pointer, right? So we're going to create all the jazz. We have the heap code to construct the list. And you can see that I have a pointer to the first element, essentially what we did before, right? We have the same data structure. Now, look carefully here. We can say that an array identifier is just a pointer to the first element. It is not exactly that, right? I made already a video about that. You can check it out if you have any doubts. Here I explained the concept of array decaying into a pointer. We can say for any practical purpose that an array name is just a pointer to the first element. So we have this scenario, right? You see that it's very similar, the thing. The name of the array is just a pointer to the first element, as well as the root pointer is a pointer to the first node. It's very, very similar. You see? The thing that changes, of course, is the way by which we can iterate over an array. And now we're going to see the difference. So to iterate into an array, it's fairly simple. We simply declare our legendary high iterator, right? We assign the value 0. And then we say while array in position I is different from 0. What do? You do your code, right? It can be like print the actual char in that position. And then you move the actual I until it's going to be in the actual \0. At that point, our loop is going to decay and we are done. Easy peasy, right? The thing becomes trickier when we're dealing with linked list, but you will see it's not that terribly complicated if you have this visual understanding. Here, I just want to emphasize that you cannot increase directly the array identifier, the array name, because the name itself is not a pointer. Make sure you understand the dance between the pointers and array. You understand very well this point, why you cannot do this operation, but you need the I variable. Now let's move to linked list. So I'm going to have my linked list in the heap, right? Then I'm going to declare another variable, which is called current. This is a convention. And then what do? I say current is equal to root. So now current is pointing to the first node, which is bad food, right? The first node is found at position bad food. And then I say while current is different from null. What do I do? Well, I perform my code that can be printing the actual member variable h, right? The char h. Then we simply update current to be equal to current next. So what is going on? Let's have a visual understanding. Current initially is pointing to bad food. Then it's gonna point to cafe baby, you see? Because it's the next of the first node. Then we do the check. Current is different from null, of course. You do your operation like printing I, and then current is equal to current next, which is that beef. So now current is pointing to that beef. We do the same, the loop, and you got the gist of it, right? Now current is equal to null, and our iteration is finished. So what is the gist of it? You understand masterfully, right? The current for a linked list is like the high for an array. That's exactly the same concept. We have a sentinel value for the char array, which is the \0 at the end, or it can be the actual size of the array. And for linked list, we have a sentinel value, which is the null at the end of our chain. But essentially, it's exactly the same thing. We have to remember, okay, I want to iterate in a linked list. So I need an I iterator, like in an array. In this case, it's going to be a pointer that I call current, or I call high. You can call high even here. Okay, so that's the main idea of iterating into a linked list versus an array. So let's just write some code to really see in practice what I've been saying. Okay, I'm gonna include stdio.h and include the standard library for the malloc. Then we have to create our node, right? So typedef struct node is equal to the member variable n and a pointer to the next element, which is equal to struct as node next. By convention is always called next, like that. And then type node. Boom. We have our building block for the linked list. So now let's create our linked list. I'm gonna create a pointer to root, and I'm gonna say root is equal to malloc size of type node. Okay, so this is gonna give me back a slot in memory with a space for node. Then I say root next. Of course, I'm not creating all the pointers in the stack for all the nodes. I'm gonna do immediately in this way. Do root next is equal malloc size of node again, and then again root next is equal malloc size of type node. Basically, we are here, right? I'm just doing the same without the node 1 and node 2 variables. Then I say root n is equal to 42. Root next, we access the next value. N is equal to another number, and we do the same for the last. So root next is equal to 21. Okay, here I forgot to put an integer like that. Then being the last one, I'm gonna do root next is equal to null. Very manually, very tedious, but just to have a really good understanding of what is going on. Then I'm gonna print all the elements. So what do I need to print? For array, I need I, right? The high iterator. For a linked list, I need current, which is a pointer. So let's just declare this current. Let's say current is equal to what? Is equal to root. So it's a pointer to the first element. And here I simply do the while loop. While current, different from null. Here I can simply say while current, essentially, because null is 0. So I can exploit the value as a Boolean value. What do? Immediately at the bottom, I do the update, right? Current is equal to current next, okay? This is essentially like the ++i for the array. And here I just want to print the actual value. So it's gonna be %d, new line, current, n, like that. So this is the final result. What do you think? Is it gonna work? Well, let's find out. So I'm gonna compile list.c, launch. I get the numbers, right? 42 and the other ones. It seems like it's working, but as you can see, the bare-bound code is not really convincing. Let's have a visual understanding again of what is going on. So I'm gonna cut this code, and I want to see this baby. So here, another marvelous source that I always suggest is ctutor. Ctutor is a marvelous tool because it allows you to really see your code. That's exactly what we want to do now. So let's have a visual understanding of what is going on here. So we start from the beginning. I have a pointer root, right? And I call the malloc. Malloc is gonna allocate space for a node. Here you can see clearly the node. And then, of course, all the other mallocs that are gonna put the address of the next node, right, in the next of the root node. We run again the code and we get all the 3 nodes usually, right? Then we're going to assign the values. So 42 root n, right? Root n. Then I'm going to say root next n. So root next n. This value is going to be 1000 and so on. And then the last one, root next n 21. So root next, we access here, next, we access here. The last value, 21. Boom. Then I simply put null in the last element, so we get a null here, as you can see. And then it is simply my printing routine. So current is going to be equal to root. Let's see that. So you see current is point the first one. Then we print the value of the first one, and then we update the value of current. Now, I don't know why there is this glitch, but anyway, you got the point. The second one is 1000 and so on, and the third is the last one, of course. Boom, we are done. Now current is equal to null at the very end. Now it works. And the algorithm is finished. As you can see, you can have a very well understanding of what is going on with this tool. You can actually see the nodes created with your code. See? So that's all for the theory part. Now we're going to do a lot of exercises to really understand all the ideas related to linked list. So now we're going to start with the actual exercises. For this exercise, we're going to use this struct, this node, a node that contains a void pointer. Void pointers may be confusing, but just change the word void to generic, a generic pointer to something. We don't know what it is. And then, of course, next pointer, right? This, of course, is mandatory if you want to create a linked list. So now let's have a visual understanding of what I'm saying. You have a pointer to something, content, which is, we don't know what it is, and a pointer to the next element. So this is what is going on, something like that, okay? So we're going to use this. So basically in this exercise, we have to return a new node with the content value initialized with the value of the parameter content, okay? So the scenario is this. I have my function that takes as an input a void star, so a generic pointer to something, probably something that is in the heap, but we don't actually know, we don't care. And now we start to code. What is the idea? What do we want to do? We want to create a new node with the content as the parameter as an input. So first of all, we are gonna create the actual node. So I'm gonna declare an actual node, type list, okay? So a pointer to that, and then I'm gonna call the malloc, okay? Malloc size of type list. Okay, now we have in the heap at the address bad food, this hexadecimal, this node. Then what do we do? Of course, after every malloc, you have to check for nulls. So you're gonna say if null equal node, return null, right? Easy. And then what you're going to do, you're going to say node content is equal to content. So what is going to happen? Well, simply this. We're going to say the content of my node is going to point to the content. And then I'm going to say node next is equal to null. Boom. So as you can see, we managed to create this new node that we can return. So we're going to return to the caller function this pointer, which is bad food. We're going to return that pointer to this node that is pointing to the actual element given as an input, as a parameter. Okay, so I think visually it's pretty simple. So in this case, we are gonna have to add a new node at the beginning of the list. Okay, so a function that doesn't return anything is gonna take a pointer to a pointer. This is the tricky part, and then a pointer to the actual new node. Let's have a visual understanding of what is going on. So we have our caller function, right? So let's pretend this is foo, the function that has a pointer to the actual linked list, as you can see, right? This linked list starts from bad food, which is the first node of the chain. The function is going to pass the address of the pointer to the first element. So this is what listed is going to take. It's going to take a pointer to the actual pointer. So it's going to take a pointer to bad food. You see? You will see why this is important. This is the scenario. We have this linked list made of 3 nodes and the new node, which is this one with address code that. Okay. Every node has a generic pointer, a void pointer to some data. So that's what add front, list add front is going to take. Is going to see a pointer to the first element and a pointer to the new node. All right, let's start. So the thing is that I want to put the new node as the new first element. It may seem tricky, difficult, but you will see it's pretty darn easy. I'm going to say as the first thing, new next is equal to at list. So new next equal at least. Just watch the code that node. and the next value is going to point to bed food, which is the first node, okay? Like that. Easy peasy, right? One line of code. And then what I'm going to do, I'm going to say at list is equal to new. So I'm going to dereference a double pointer. So I'm going to access the pointer, which is at the function foo, the color function, right? And I'm going to change the value there to point to new, which is code dead. So let's see the animation. This is going to change to code dead. Now the function, the color function is going to point to the new node. That's it, my friend. 2 lines of code. Done. Easy peasy. Now let's see better what we get removing those arrows. And as you can see, we managed to change the list, right? Now the new node is the first one with 2 lines of code. And of course, before doing the actual operations, list at front needs to check if list and new, right, are not null pointers. So I check if list is an actual pointer, is different from null. Here writing different from null is redundant. So I can actually write directly if list and new. The next exercise is going to be list size. So again, let's have a visual understanding. We have this function that takes as an input a pointer to an actual linked list, as you can see, and it has to return me back a value. So it's pretty easy. We understood from the theory part how we can iterate easily into a linked list. Essentially like an array, we just have to use an auxiliary variable, which is current, right? Which is like the high for the arrays. So let's see what is going on here. I'm going to declare a counter or a size, call it as you want, and counter is equal to 0. Always remember to initialize the variables. Then you say while list is different from null. So I'm going to use directly the pointer given as an input. What do? I say counter plus plus. I'm going to increase the counter, and then I'm going to increase directly list. So I'm going to use this local pointer as the current you saw in the theory part, in the initial part. Okay, so that's basically the code. So let's see the animation. So initially list is pointing to bed food, which is the first node of our linked list. So we are going to increase the counter. It's going to be 1. Then we're going to say list is equal to list next. So now list is pointing to the next node, which is cafe baby, right? Increase the counter again by 1. And then we change list to the next node, which is that beef, the last one. Increase the counter again. And then finally, list is going to be equal to null. So the loop is finished. Then we simply say return counter. Don't tell me this is complicated. This is pretty easy, right? If we understand how to iterate in a linked list, this is an ice cream vanilla, right? All right, other function is going to be list last. We just have to find the last node of the linked list. All right, so again, our function is going to take a pointer to the actual linked list. And what do we do in this case? Well, the pattern is similar to counting all the elements. The only thing we are doing here is the check at the while. We say while list next is different from null, not list itself. List next. So we are checking if we are pointing to the actual last element of our linked list, because our last element has the next pointer equal to null. So let's see the visualization. We say list equal list next. I have initially the pointer list pointing to bed food. Then the pointer points to cafe baby, the second one. As you can see, list next different from null. In this case, it is different from null because it is that beef, the next pointer. So I go on the next node. And this time we check list next different from null. In this case, it's not true because the next is equal indeed to null. So the while loop is going to end. We're done. This is the pointer, the actual pointer that we want to return, that beef. So we're going to return that, return list. And of course, we have always to check for null. So if not list, we simply return null. That's it. That's the code to find the last node and return a pointer to that. Other function is going to be list add back. So basically it's like the add front, but just in reverse. We have to append a node. If you're familiar with Python, there is this method append. And yeah, let's do that. So the function again takes as an input a pointer to a pointer. So we have this scenario in which list points to bed food, which is a pointer to the first node, of course, and then a new pointer. This one is going to be appended at the end of our linked list. All right, so the pattern is pretty similar to at the front, with minor differences. So what are we going to do in this code? Initially, we're going to declare a pointer to the last node, okay? And then we're going to say in the usual control, you're going to return because we cannot do anything basically. We have a invalid pointer. On the contrary, if null is equal to at list, okay, so here is written, if the caller function gave me a list which is null, it's an empty list, what do? Well, you simply say at list is equal to new, right? Because we have to append to that list the new value. So if the list is empty, you simply say, okay, at null is going to be equal to the actual new node to append. This is not the case, right, by now. So what we're going to do, we're going to say last is equal to list last, the function we just created, right, to find the last node. So now last is going to point to the actual last node, which is that beef. And then what are we going to do? We are going to say last next is equal to new. So what is going to happen? This exactly. We're going to cancel the next value null. And now this last pointer, that beef, is going to point to code that, which is essentially the node we wanted to append, like that. So we have this scenario here. See? Now we clean a little bit the scene so we can see better. And effectively, with this code, we managed to really append the node. You see? Take your time to visualize what is going on, but essentially this is what happens. We need a pointer to a pointer because we eventually have to change the actual value of the pointer in the caller function if the list is null, right? If the list is empty. I think it's not terribly difficult, right? All right, new function is going to be delete one. This function basically has to take a node and free the memory of the node content using a function given as a pointer function. So this is the scenario. We have delete one that takes an input, a pointer to a list, which is, let's say, only one element for the sake of argument, and a pointer to function. This can be tricky. I already made a video. I'm not gonna go into details here, but it's not terribly difficult. If you have any doubts, I suggest you to have a look. So what I'm trying to do, I want to delete one node. That's it. So I'm gonna do if not list or not del. Basically, if I have a null pointer for the list and a null pointer for the function, I'm just gonna return. This is a mistake. Then I'm gonna say delete list content. So I'm gonna call the function on the content of the list. Delete is gonna be much probably a wrapper for a free. So what is going to happen is this: I'm gonna release the content pointed by a void, right, from the content pointer, and then I'm gonna say free list. So I'm gonna basically free the actual node. So I'm gonna get this, boom, I'm gonna free everything. Everything is clean, and I managed to delete one element. That's basically it for this function, these lines of code. Okay, now we're gonna create a function list clear that is gonna delete and freeze the given node and every successor of the node. Use it, the function, give it as a pointer to function. So again, let's have a visual, which is the best thing. Our list clear function is taking a pointer to a pointer, again, pointer to the first node, right? So we have this scenario. List is pointing to the pointer that is pointing to the first node of our linked list, which in our case is bad food, the actual hexadecimal, okay? Then we have a pointer to function, like before. The function is trying to clean all the actual nodes, right? It's trying to clean all the actual nodes from the given address. So let's start to code. I'm gonna, first of all, create a current, right? A current pointer, which is like the high of the array, just to iterate over a linked list. Then this time we have something different. We have a new variable, which is a temporary variable, right? We're gonna see very soon what is the goal of this variable. Then we are gonna, of course, check again for potential null pointers. If this is not the case, you're gonna say current is equal at least. So let's see what is going on. I have current that is pointing to bad food, which is exactly at least, right? Pay attention here that at least is actually bad food, right? Is the pointer to the first node. So I have my current that is pointing to the first element. Then what do? I say while current is different from null. Here I can also say while current, just to be pedantic, I say different from null. I say temporary is equal to current. So temporary is gonna point to bad food. Then I am gonna update current is equal to current next. Okay, so my current now will point to cafe baby, the actual next node. And then what I'm gonna do? Well, I just want to free, I just want to clean everything. So now I will call the function delete to what? To temporary, right? To temporary content, because temporary is pointing to the previous node, to bad food. So now what is going to happen? Well, we're going to call the function delete on temporary content. So poof, that is gonna be freed, and then I'm gonna call free to actual temporary. So poof, we're gonna free the actual node. So you see the temporary is very, very useful to free stuff. I cannot do that with current. I cannot go on a node and then free that. If I free the current node, then I don't have any more access to the following node. You get the catch. Let's see again the animation. Now temporary is equal to current again for the following iteration. Then again, current is going to be updated to the following node. So it's going to point to the next one, and then clean. We're going to clean again, delete the actual content and free the actual node. You see? We move on. Temporary is equal to current again, and current this time is going to be equal to null. So we are going to at last delete the content of the last node and then free the last node. Boom. As you can see, we managed to clean everything, to delete everything inside the heap, so we don't have any leaks. Now what do? Well, we simply say at list is equal to null. So we're gonna change the value of list in the caller function. That's why we need a double pointer, because I want to change that value there. I'm gonna say, hey, the list is clean. There is no anymore the list. So boom, I'm gonna change that value. And now we are done, right? Everything is clean. The list pointer in the caller function has been set into null, and we are ready. That's it. That's our clear function. As you can see, I need a temporary variable to make the trick in the while loop. I cannot free the current node, otherwise I don't have access to the next node. That's the gist of it. You have to understand this point. So we're going to use a temporary variable. It's a little bit like the swap function, right? In which we use an auxiliary variable to stock the data. Otherwise, we're going to have an overwrite, right? We have two variables. We stock one in the temporary variable, then we do the swap, and then we take this variable and put here. If we do immediately the swap, we're going to have a crash. We're going to have erasure of data. All right, I guess it's pretty understandable if you have a clear visualization of what is going on. The last thing I want to tell you is that you should probably use delete one here, because deleted free is basically the delete one function. So we can make the thing more abstract. Okay, now we have the function list iter, which is basically a function that will apply the function f to every node of the linked list. As you can see, we have a pointer to the first node of the linked list, which is bad food. And now we're going to do that. So what is going on here? Well, first of all, I'm going to say if not list or not f, basically if these are null pointers, we don't care, we go back. If we have valid pointers, namely these are not null pointers, we do a while loop while list is different from null. Now you know this pattern super well. This is just iteration. And you call f to every element of the node. So you call f list content. You see? So what is going to happen? Well, a function is going to be applied to the element. Here the animation is going to show you just the box jumping to silly show that something happened. And then we update LST to list next. All right, simple iteration. We move on. We go on the cafe baby node. We apply the function to the box. When we move on, to that beef node, apply the function, and then finally list is going to be equal to null, and we are done. We managed to apply the function to all the elements through iteration using this pointer, and that's pretty simple, right? I guess. All right. That's it for the list iteration function. So now it's time for the final boss, which is list map. This function takes a pointer to the list and a pointer to two functions, right? Here you can see that list is pointing to the linked list. And these two functions are f and del. Well, del is a function to delete, right? The content. In the case, we have to delete stuff. You will see while coding. In this function, we have to create a linked list, which is peculiar to the one given as an input, but with all the elements, all the contents that have received the function f, right? So all the contents will be different because of this function. Let's see, the animation is going to be simple. So what do we do? Initially, I say new list. This is the actual new list that I will return. Then I'm going to say type list new node. Basically, this is a pointer to a new node. Every time I'm going to create a new node and apply the actual function f to the content. Then the actual control, if not list, we have no business here. We're going to return. Then I say new list is equal to null. Of course, I have to initialize the new list. This is very important. After that, I'm gonna do a while loop until list, so until this pointer is not exhausted until it's different from null. And then I'm going to say if the function is not a null pointer, you're going to call the function listNew, which is a function to create a new node, right? We did at the very beginning. I apply the function f that takes as an input a void pointer, which is list content, right? Now list is pointing to the first node, so I take actually the first box, as you can see, and apply the function f. F is going to return me back a void pointer that is going to be the input for the function listNew, right? I think it's not terribly complicated. Otherwise, if the function is a null, I will simply create a new node. So the function, the lists are going to be specular. I just implemented this way. Arguably, it is not correct. Maybe if the function is null, I just have to return null. I don't know. I just did in this way. I think it works. So that's the important thing. So I understand this line, right? We're going to create a new node that takes as an input the void pointer, the element pointed by the void pointer, but processed by the f function given as an input. All right, so let's see the animation. I have this new node that is pointing to the newly created node, and the element pointed by star is changed thanks to the f function. Now I just flipped the box to show that the thing is a little different. Okay, then what do? I say if not new node. Of course, I control if the new node listNew function has failed. You just call listClear, the function we previously made, right? And I pass the address of the new list. So this will clear everything, all the nodes that we have already made. It's gonna be a cleanup function. And I pass as a pointer to function delete, all right? And then I simply return. We have no business here. This only if the listNew function fails. Then I'm gonna say list add back. So this is a function to append, right? This is gonna append a node to the list. So what is going to happen? Well, new list now is going to point to the new node just created, right? And then I'm going to say list is equal list next. So I'm going to move on. I'm going to move on the pointer. So I go to the second node, and then we keep going on, right? We are going to create a new node with the function applied to the void pointer. We do the control if the node is equal to null, and then we are going to append. So now we have the first node that points to the new node. We increase list. Now it's going to point to the final node. We create a new node again, the same thing as before. And then we just call list add back. So we append this and we are done, right? Now list points to null. And then we simply return the actual new list that has been created. All the nodes have been successfully created. The function f has been applied to all the nodes, and we are done, right? I think that with the visualization is not terribly difficult, right? I hope this is clear, and that's it for this challenge. I really prompt you to use CTutor for these exercises, which is pretty powerful to understand everything that is going on. All right, that's it, my friend.